Welcome to Advanced Digital Signal Processing. This is a graduate level course in signal processing, so a few things to get out of the way. First, I assume as you're taking this course that you've had linear algebra. We will be using linear algebra extensively, but I will also provide some review of each of the concepts as we get to them. Next, it is a signal processing class, and it's assumed that you've been exposed to signal processing at some point. If you have not, I can say that others before you have taken this class without having signal processing experience, but it will require a little bit more work on your part, particularly in this first section where we're going to quickly go over some of the background concepts. If you find yourself in any of those situations and you're not sure if this is the right class for you, or if you have questions about how the material is going to be run, please feel free to reach out to me. We're going to start out today talking about the Shannon-Nyquist sampling theorem. If we're going to be doing signal processing, we want to, in particular digital signal processing, we want to be sure that what we are doing has any relevance to the real world. And the Shannon-Nyquist sampling theorem is that critical connection between what we're doing and the real world, if you like. So sampling is simply converting some continuous signal into discrete samples, as shown here in the figure. In general, we would have xn, which is the sampled signal over on the right, is defined as xc, evaluated at t is equal to n times some sample period, capital T. So capital T is our sampling interval or sampling period, and so we just evaluate it like that. One of the things that I try to do, every once in a while I get sloppy, and I apologize ahead of time, is if we are dealing with discrete signals, I use square brackets, and if we're dealing with continuous signals, I use parentheses, like so. So T is our sampling interval, or sampling period, and in practice there are many devices that perform this basic function. We've called this a C to D converter, continuous to discrete, but if you go look online to try to buy one of these, you'll find them called analog to digital converters instead of C to D converters. There's a difference. For example, an A to D converter can't perfectly sample something at an instant in time. We have actually some limitations due to Heisenberg's uncertainty principle. When we try to implement this and we try to get something to sample exactly, we actually have to measure a signal that's represented by electrons or some other physical quantity, and getting it exactly right is difficult. So we use C to D, meaning that we're going continuous to discrete, and it's ideal, whereas analog to digital kind of encompasses some of the realities. The other really big reality is that analog signals, when converted to digital signals in real life, have a finite number of bits in their representation. So the amplitude is quantized. But for now, let's start with the ideal case, and we'll deal with other issues as we go along. So questions that should come up here. The first is, can you reconstruct our continuous signal from the discrete signal? 2, the answer to that is sometimes. The second question is, how do you do it? So the answer to question number 1 is when our signal is band limited, meaning that the frequencies in that signal are 0 beyond a certain point. I'm introducing some more notation here, but I'll explain it as we go. Then we can perfectly reconstruct xc of t from x of n. So first, let's go in here and define what xc, that's a capital X, j omega, really is. This is the continuous time Fourier transform, defined as the sum over all time of e, or x, the signal, projected onto this. Okay, so a few things. Excuse me, this e to the minus j capital omega t is a complex exponential. J is the imaginary number. And it is equal to cosine of omega t. Since we have this negative sign out there, we get a minus j sine omega t. So it turns out that the complex exponentials form an orthogonal basis in this space, and we'll talk more about that in general later. So we're really projecting our time signal onto this frequency basis. Since it's infinite in length, there are infinitely many, and so it's indexed not like the basis functions that you ran into in linear algebra where you might have n dimensions. Here it's continuous. And so we get this representation as a function of frequency. So omega here is frequency in radians. Okay, so when x is band limited, as in when the Fourier transform is 0 above some certain point, then we can reconstruct xc of t from x of n as long as we sample twice as fast as the highest frequency. So the sampling rate it's actually greater than twice as high as the highest frequency in xc of t. So that works out to 2 pi over t must be greater than 2 times omega max. So this is actually represented right there in the same thing. So this is the vaunted Nyquist criterion. So you notice up above that we talked about the Shannon-Nyquist sampling theorem, and Nyquist is usually the one referenced with this, but Shannon had some important little additions to make, and we can talk about some of those later. But primarily, if you have something that is band limited in a narrow band, as opposed to such as between two frequencies, not just below a frequency, then the Shannon theorem lets you actually get away with sampling at a little bit lower rate as long as your rate is twice as high as the band width of this bandpass signal. Okay, so the second part is, this question was, how do we reconstruct this signal? And the answer to that is we use a sync interpolator. So, what does that mean? Well, I'm going to use R here for reconstructed. That means x of t is going to be equal to sum over all samples, where we take each sample and we multiply it by a sync function, which is essentially this, pi of t minus, and we're going to shift that sync function so it lines up to the right point in time. That's the t minus nt, and then the argument is down here below. So when t, little t, is equal to n times capital T, the argument of the sign evaluates to 0 and the denominator evaluates to 0. But using L'Hopital's rule or any other method you might want to come up with, we find that this evaluates to a value of 1. And often, in fact, I'm going to write this slightly differently because we're going to explore other functions for reconstruction. And so we'll do gt t minus nt. So this is a shifted version of the sync function. Okay, so we have some problems with this that you may remember, or maybe it's new and you just spotted them right away. The one is this sync function is going to die out as 1 over t, which means it never goes to 0 until t goes to infinity. So we're in essence adding up a bunch of functions with infinite support. And in fact, a bunch isn't quite accurate. It's an infinite number of functions with infinite support. And so from a practical point of view, this can be a little bit troublesome. But it's actually what's required for the ideal reconstruction. I'm going to add a picture to this. Let's see, picture, online lectures. Let's start with sync block. Okay, so here's our sync function. And it turns out that the Fourier transform of the sinc function is a rectangular box here. And so in one sense this makes some intuitive sense, in that what we're doing is we're taking these samples and we're filtering them with an ideal low-pass filter to make sure that when we reconstruct our signal, we get our band-limited signal back. And so this is what this is looking like. So let's see what it looks like when we recreate a single sample. Let's see. Okay, so here we have this single sample as 0, and we want to reconstruct the continuous time signal, and it looks like, well, a sinc function, because that's exactly what our equation predicted. But there are a few things to pay attention to. One is, these are the positions where we have all our other samples, and in this case all our other samples are 0, but the sinc perfectly passes through 0 right at those points. Therefore, when we reconstruct this signal that was just a single sample as 1 at 0, we get something that is 0 everywhere else. In some way this should be satisfying, because if we were now to take this sinc function and sample it again at the same points, well, all these fuchsia colored points are going to evaluate to 0, and the only non-zero point will be this yellow one, exactly where we came back and where we started from. So now let's look what happens when we have multiple samples in our X. So if we start with an X that has multiple samples, and here we've got one with 4 samples, and I apologize, I'm fighting a bit with my OneNote. I think if I do that, we'll just put it down here and everything should be okay. There we are. When we now do our reconstruction, remember the reconstruction involved adding up a bunch of sinc functions. I'll make that one a little bit bigger so you can see the detail of what's going on. You can see that each sample is represented by a different color. We have blue, green, red, and kind of a teal color. And they all pass, the respective sinc functions all pass through 0 at every other sample. But when we're all done adding those together, we get something like this. Now this is very different than what you might expect if you were to just say create a continuous time signal by interpolating between those points. It's got some strange little hiccups in there, and it rings on forever even though you started out with something that only had 4 samples. However, this version of the signal is band limited. And so while this might not be the best way to reconstruct, say, an image, it is the best way to reconstruct something that's band limited. And that's what we typically are concerned with. So that brings us to the fundamental theorem of DSP. which is if xc of t is band limited to b, and we describe that, but just for completeness we'll put it here. It can be perfectly reconstructed from samples spaced t less than or equal to, actually put a less than, pi, oh, it's less than or equal because we have the strictly less than up there, apart. And this is the best part. I love it when a proof is not just an existence proof, but actually shows you how to accomplish it. I say that a little bit tongue-in-cheek because this shows you how to accomplish it, but if you're actually to try to implement this in practice, you'd better have a really fast computer, because it's going to have to do an infinite number of adds at an infinite number of points, which tends to take a long time. Okay, just a few points here. This reproducing formula for reconstructing our signal is very useful theoretically, but as I hinted, it's not very useful in practice because we have to do an infinite number of sums, and we are summing up signals, these g of t, these sync signals that are infinitely long. So while it is ideal, it doesn't, it's not very ideal to actually implement. So we will look at some other applications. I just wanted to mention other approximations to this. One is that we can actually use some signal interpolating function other than g of t, which gives us something that's really close, arbitrarily close, to our perfect reconstruction. And I found a paper some years ago where these guys had worked out a function that was very, very close to being perfect reconstruction, but it was easily computable. So I was really excited about this, and reading the paper, all looked fine, but there was a typographical problem, and after explaining their methodology and everything else, the equation that gave the interpolating function was broken, and I couldn't see what it actually was. But we'll find that there are other methods that we can do reconstruction. But the best thing is that we know it's possible to do it perfectly. Therefore, we can figure out any changes necessary that we can do to make it computable and know how close we are to perfect reconstruction. So